Very good morning to all of you. So today's topic of discussion is from Unit 2, that is energy bands in semiconductor. First of all, I am Dr. Rakhi Sharma, Assistant Professor in Electronics and Communication Engineering Department, Akgec Engineering College. So today I am here to discuss this topic, that is energy band in semiconductors, which is from Unit 2. And starting with this introduction, first of all, the basic introduction of electronic devices. They are those devices that allows the control the flow of current for the purpose of information processing and system control. According to the nature, we classify them as active or passive devices. Based on the electrical conductivity, we are classifying our electronic devices as conductors, semiconductors and insulators. Conductors are those whose conductivity is very high and they provide very ease in the flow of the charge carriers. That means they provide high gain as compared to semiconductors or insulators. The energy gap is zero, and the examples are insulators of conductors are basically copper and gold. Semiconductors, their conductivity is in between the conductors and insulators. The energy gap is around 1.2 electron volt. The basic examples are silicon and germanium. Insulator, their conductivity is very low. The energy gap is more than 6 electron volt, and the examples are glass and rubber. Now coming on to the types of semiconductors, the first are the intrinsic semiconductors and the second are the extrinsic semiconductors. Now, starting with the types, the first category of semiconductors of intrinsic semiconductors, which is the pure form of semiconductor. That means we are not adding any kind of impurities in case of intrinsic semiconductors. So, the number of electrons is equal to the number of holes in case of intrinsic semiconductors, and the examples of intrinsic semiconductors are basically silicon and germanium. Now, what are the extrinsic semiconductors? Semiconductors whose electrical properties can be modified or can be altered by adding the impurities are called extrinsic semiconductor. The process of adding the impurity is called doping. So, what is the need or essential or significance of this doping is that what is the basic need of doping? They are essential for creating the electronic devices because they allow the controlled manipulation of electrical conductivity. Because by increasing or decreasing the amount of doping impurity, we can easily control or manipulate our electrical conductivity of our device. So, this is the basic need. Now, the extrinsic semiconductors are further classified into two categories. The first is of N-type semiconductor. It is a semiconductor material that has been doped with impurities to increase its conductivity. It is created by adding the pentavalent impurities. The examples of pentavalent impurities are phosphorus and arsenic to the purest form of semiconductor. So, the majority charge carriers in case of N-type are the electrons. This is a diagram of N-type semiconductors in which we are basically what we are observing in this case, we are adding a pentavalent impurity, that is your phosphorus, to the purest form of semiconductor, which is silicon. So, by adding this pentavalent impurity, we are getting the N-type semiconductors in which the majority charge carriers are basically your electrons. Next is of your P-type semiconductors. What are P-type semiconductors? It is a semiconductor that has been doped with the impurities to increase its conductivity, and they are formed by adding the pentavalent impurities. The examples of pentavalent impurities are basically boron and aluminium, and in this the majority charge carriers are holes. This is the diagram of in case of P-type. What we have observed is that aluminium is the trivalent impurity which is added to the purest form of semiconductor to obtain your P-type semiconductor. and this presence of hole, or we can say that the vacancy created by an electron is represented by this hole. So, in this the majority charge carriers are holes. This is the concept of Fermi level, which is the most important or essential topic of particularly of unit 2, and basically it plays a vital role in differentiating your semiconductors, as we see in this diagram also. This basis on this Fermi level we are differentiating your intrinsic and extrinsic n-type and p-type semiconductor. So, coming on to what is the basic definition, or what is the Fermi level? The Fermi level is basically the highest energy level that has been occupied by electron, or we can say that it is the energy level where the probability of occupancy of an electron is almost 50%. So, this is a basic definition of Fermi level, and what we are observing in this diagram is this case of intrinsic semiconductors, this Fermi level is basically in between your conduction band and valence band, that is, it lies exactly in between these two bands. So, mathematically we can give the expression of Fermi level also, which can be given by EC plus EV by 2. So, that is a mathematical part I have not discussed in this, that EF can be given as EC plus EV by 2. What is EC and EV? EC and EV are basically representing the conduction band edge. This edge is particularly representing this EG, particularly your EC, and this edge is particularly representing your, basically this edge is representing your EV. That is, the bottom of the conduction band edge is representing your EC, and this top of the valence band is representing your EV. And this EF is particularly given by the average of EC plus EV by 2. Next, moving on to the n-type. In case of n-type, this Fermi level is close to the conduction band edge, or we can say that it is lying between your donor level. Donor level is basically represented by ED, and this is EC, this edge is EC, and this is your donor level ED. So, we can also say that EF is exactly lying between your EC and ED, or in other words, we can say that your EF, that is the Fermi level, will be close to the conduction band in case of n-type semiconductors. Now, for the p-type semiconductors, what we are observing is that it is in between your, particularly your EV, and your acceptor level is EA, and this acceptor level is represented by EA. The position of Fermi level is in between your EA and EV, or in other words, we can say that it will be close to your valence band in case of p-type semiconductors. So, this is all about the position of semiconductors. We also cover in the next lecture its derivation, how it lies in between your conduction band and valence band edge, how it will be close to the donor level or the conduction band edge, and how it will be lie in between your acceptor level and valence band. That will be discussed in the further lectures, their mathematical derivation. This is the basic definition of Fermi level, which I had discussed earlier also. That is, Fermi level is the energy level where is the probability of finding the electron, or the probability or occupancy of electron is almost 50%. Fermi level in case of intrinsic semiconductor. In intrinsic, it is lying exactly in between your conduction band edge and valence band edge, and we can say that in this case your number of electrons is exactly equal to the number of holes. This is the mathematical expression for the Fermi level in case of intrinsic semiconductors, where EF is basically representing your Fermi level, EC is representing your conduction band edge, and EV is the valence band edge, and their average is basically giving you the position of Fermi level, that is EF. Now, what are the factors that are influencing your Fermi level? The first factor is your temperature, the next is material band gap or the energy band gap, and the last is the effective mass. temperature, as the temperature increases, the intrinsic carrier concentration increases, but what happens on the EF is that it remains near the mid gap. There is a difference, but a slight difference is observed in case of the changes in the position of Fermi level. Next is the material band gap. It basically determines the exact position of your Fermi level. The third is the effective mass of electrons and the holes, which can slightly shift the exact middle position of your middle position. So, the major effect is particularly of the material. The second one is of effective mass and the last one is of temperature. So, these are the factors that are influencing the position of this Fermi level. The next is the energy band diagram. Energy band diagram at 0 Kelvin, the Fermi level lies between the valence band and the conduction band. At room temperature, it will be close to the mid gap. These are the carrier concentrations, basically electrons in the conduction band in case of N type, in case of P type. What we are representing is this: N is the number of, that is the concentration of the free electrons, and P is the concentration of free holes. So, we are representing this carrier concentration in terms of the position of the Fermi level. What are these NC and NV? NC and NV are basically the effective density states in the conduction band and particularly in the valence band. And EF is representing your Fermi level. So, what we can conclude from this, these are the carrier concentration that can be find out from this N type and P type semiconductors, that how much there will be concentration of number of free electrons and what will be the concentration of number of free holes. That will help in determining your carrier concentration for N type and P type, in which the major role is of particularly the position of the Fermi level. This is the intrinsic condition that we have discussed earlier also, that is the concentration of number of holes and electrons is same, which is equal to the intrinsic carrier concentration Ni. So, this is all about the mathematical expression. We have just equate the expressions of number of free holes and number of free electrons. This is all about the derivative part, mathematical derivation. Now, this is the effective mass relationship, as what is the difference, basic difference between the rest mass and the effective mass of an electron. Effective mass of an electron is basically the mass of an electron when it is interacting with all the atoms and the particles. So, how it is related with particularly your density states, which are Nc and Nv. M star is representing your effective mass. So, this is all about the expression for the case of Nc and Nv in terms of effective mass. Now, the interpretation comes, what we interpret from effective mass or the rest mass. What will be the effect of temperature? As we increases the temperature, how much there will be a shift in the Fermi level? That's all about in this interpretation. What we are observing is that if the product of the effective mass with the holes and the product of the effective mass with the electrons, if the condition is this, then we can say that your Fermi level, that is EF, is exactly in between your conduction band and valence band. Next, if your density states in NV is less as compared to the NC, we can say that EC shifts slightly below the mid gap. That means it is shifting towards your valence band or valence band edge. That means towards the EV. Next, that is of silicon at the temperature of 300 Kelvin. The change in the position of the Fermi level is that EF is approximately 0.01 electron volt below the mid gap. That means there will be a decrease in the position of the Fermi level, which is around 0.01 electron volt. Now coming on to the applications of semiconductor devices, they are widely used in diodes, transistors and integrated circuits. Thank you. So that is all the part, or summarizing this lecture is that in this lecture I have basically covered the basic introduction of electronic devices, their classification, and particularly my emphasis is on energy band diagram for the conductors, insulators and semiconductors. And the most important topic of this unit is particularly is the position of the Fermi level, in which we have discussed how this position of Fermi level is differing as we are moving from intrinsic to extrinsic semiconductors, or the position of Fermi level, how we classify them in case of intrinsic, N-type and P-type. So, the major emphasis in this lecture is particularly on the Fermi level, and conceptual wise or for the preparation wise also we have to go through the mathematical derivation also, in which we derive the mathematical derivation for intrinsic and for the extrinsic semiconductors that we cover in the next lecture. Thank you.